Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Hello, and welcome back to Stories from Space. I'm your host, Matt Williams, and today I want to discuss going nuclear in space. The promise, the challenge, and the prospects of nuclear propulsion. What are the particular barriers to its adoption? And what is the level of technological readiness? When can we expect to see this technology becoming a part of long-duration deep space exploration missions? Now, development of nuclear propulsion concepts, it goes all the way back to the early space age, and some very, very interesting ideas were proposed around that time. And work continued well into the Apollo era and even yielded several prototype nuclear reactors. However, with the closing of the Apollo era, a lot of this work was shelved indefinitely. And with the renewed era of space exploration now upon us, this research is once again being picked up, dusted off, and reconsidered and put back into development. In particular, space agencies like NASA, the European Space Agency, Roscosmos, China, all the major players, they're looking at nuclear propulsion to accomplish all of their long-term objectives in space, which include going to the moon, either back to the moon or for the first time, as the case may be, and sending crewed missions to Mars. And not just Mars, of course, but to any location in deep space, going to Venus, to Mercury, to the Asteroid Belt, to the outer solar system. Nuclear power is seen as a solution to just about all the challenges that these missions would entail. And for obvious reasons. Among the benefits of nuclear propulsion, you have almost unlimited energy density, the slow decay of uranium or plutonium or another radioactive isotope. It can provide consistent energy to a propulsion system for years at a time. It is based on technology that has been endlessly tested, validated, and multiple applications have been made in the past few decades, ranging from nuclear power plants to nuclear subs and nuclear surface ships, like aircraft carriers. Adapting it to space would not represent much of a technical challenge. And prototype reactors were already built and tested in the space age. And best of all, it offers shortened transits. What could take months using conventional propulsion would take weeks using nuclear propulsion. And this would also cut down on the amount of time that the crews have to spend in microgravity as they're traveling between celestial bodies. It cuts down on the amount of radiation they're exposed to. So it has immense benefits as far as health concerns go, and can allow for more rapid missions and follow-ups. In short, nuclear propulsion carries with it the promise of greater solar system exploration, not just with robotic missions, but with crewed missions. So as the space programs of the world, as they contemplate their next big moves, which include the moon, but of course are looking beyond that, they're essentially repeating what NASA and the Soviets had contemplated back during the space race. They both had their eyes on the moon, but of course they contemplated what the next steps would be beyond that. And whereas the space race ended up costing a tremendous amount of money, and once it culminated with the Apollo missions, it really began to slow down and focus more on the near term and the affordable. The ambitious plans that we've set for the near future, going back to the moon in the 2020s, establishing infrastructure there, then going on to Mars. These present a real opportunity for realizing that technology, and the fact of the matter is we may not be able to accomplish these objectives without it. So, to give you a primer on nuclear propulsion and what it entails. During the earliest years of the space race, in the late 1950s and early 1960s, the U.S. Air Force, NASA, and DARPA came together to propose a very interesting concept known as Project Orion, otherwise known as nuclear pulse propulsion. And so, in an age when nuclear weapons were becoming prolific and ubiquitous, when the United States and the Soviet Union were both producing an endless amount of nuclear devices and looking for ways to send them farther and make them more destructive, scientists got together and discussed how these could be used for peaceful purposes, for the purposes of space exploration. And Project Orion is what resulted. So this lasted from 1958 to 1963, and the idea was you'd have a spaceship, a rather large one, with crew modules in the front, a very large payload section, which would be used to house hundreds or even thousands of nuclear devices, and these would be dropped out of the back of the spacecraft where they would detonate. And the shock waves created by those detonations, they'd be absorbed by a push plate on the rear of the spacecraft, which would transform that momentum into kinetic energy, so basically a momentum transfer that would speed the ship up until it reached a fraction of the speed of light. So this concept was intended partly as an interstellar exploration concept, but also for interplanetary missions. The speed could be tailored based on the number of nuclear devices. The size of the ship would be designed to reflect that. And everything about this was obviously very brutalistic and risky. And what's more, it became infeasible after 1963 because of the partial test ban, which the United States and the Soviet Union and other nuclear powers signed to ban the testing of nuclear devices in space. So the idea was abandoned, but it did establish a certain precedent. Since then, other attempts have been made, design studies and projects that looked at various types of nuclear reactions and how they could be used to create spacecraft capable of making interstellar journeys or interplanetary journeys in a respectable amount of time. And this includes Project Daedalus, which was a study conducted by the British Interplanetary Society between 1973 and 1978. And this consisted of an uncrewed exploration probe, which would be interstellar, and it would rely on fusion reactions. And this project officially ended by the late 70s. And this idea would eventually be picked up again by the British Interplanetary Society and their partners at the Tau Zero Foundation, which in 2009 launched Project Icarus, which was basically a scaled-down version of the concept. So in both cases, these relied on deuterium pellets, basically a form of hydrogen that is heavier because it has a neutron in its nucleus. These would be fused by lasers or some other confinement forces until the pellets fused and released a tremendous amount of energy, which would then be channeled through exhaust nozzles to create propulsion. Now, these had something in common with Project Orion in that they were primarily intended as interstellar concepts. And in the case of Daedalus and Icarus, they're also uncrewed. These were exploration probes that would be intended for exploring nearby star systems. Closer to home, NASA, the Soviets, and other space agencies ever since the space race, the research that they have conducted had to do with interplanetary concepts. What's more, unlike Daedalus, Icarus, and other very far-seeing and theoretical ideas, these did not depend upon future innovation or future technological breakthroughs in order to make them feasible. And of course, they're also vastly more cost-effective because they rely on technology that has a very long track record of proven effectiveness and capability and have been used for decades here on Earth. And proposals for nuclear spacecraft that are interplanetary in nature, they generally fall into one of two categories. On the one hand, you've got nuclear thermal propulsion, or NTP, which consists of a nuclear reactor heating up hydrogen or deuterium fuel, which then expands and is channeled through exhaust nozzles to generate thrust. And compared to chemical rockets, it combines high thrust with twice the propellant efficiency. And on the other hand, you've got nuclear electric propulsion, or NEP. And for this method, a reactor is used to generate electricity to an ion engine or Hall effect thruster, which then uses magnetic fields to ionize inert gas like xenon, and then channels them through nozzles in order to generate thrust. Now, whereas NTP provides greater initial acceleration, NEP is vastly more fuel efficient and provides a very, very steady stream of acceleration over time. A third possible category is what's known as bimodal nuclear propulsion. So this is a system that would rely on both a nuclear thermal and a nuclear electric propulsion system, and these would likely be combined in order to provide greater initial thrust and then braking thrust upon reaching the destination, plus a smooth, steady-going acceleration in between. Right now, most development efforts are focused on nuclear thermal propulsion applications, mainly because when it comes to missions to Mars, which is what most of these concepts are primarily being developed for, a nuclear thermal system offers the advantage of more rapid transits. And the fuel requirements are in keeping with an NTP system there. They're not prohibitively high to the point that you'd want to have the incredible fuel efficiency of a nuclear electric system. So, in terms of missions to Mars or destinations that are within or just beyond the cislunar system, say to near-Earth asteroids, nuclear thermal is likely to be the more popular option. But with missions beyond that, to the asteroid belt, to the outer solar system, nuclear electric and bimodal systems are likely to become more common. So to give you a sense of the timelines here, as I said, the NERVA reactor and NERVA engine was a concept that came out of the Apollo era. But by the 1990s, efforts to develop an actual nuclear propulsion system, they began to resurface because at this point, NASA was contemplating the next big steps beyond the space shuttle era and the International Space Station. And the first proposal to come out of this was the Mars Direct study, which, as we explored in a previous episode, that was the work of Robert Zubrin, Martin Marietta, and David Baker. And they produced a study that called for the development of a new super heavy launch system that had a nuclear first stage on it. So the first stage of the rocket would have a nuclear thermal propulsion system, and this would reduce transit times to Mars to 3 to 4 months from the 8 to 9 months using chemical engines. And this was similar to what Wernher von Braun had recommended back in 1969 when he proposed how NASA could send missions to Mars by 1980 using Saturn V rockets that would be equipped with a nuclear shuttle. So the idea of reaching Mars within 100 days, that first emerged by the early 90s thanks to pioneering research like this. And from 1993 to 2009, NASA drafted several proposals, which were known as the Mars Design Reference Architecture reports. And by 2009, they had their fifth draft out, and all of these featured nuclear thermal rockets to one degree or another. And then in 2013, NASA's Marshall Space Flight Center, they conducted a series of engine concept studies, and they recommended that interplanetary travel from Earth orbit to Mars orbit and back, and to destinations beyond, could be accomplished with nuclear thermal engines. And by 2017, the Marshall Space Flight Center, they reignited their whole nuclear research through what's known as the Game-Changing Development Program. And by 2019, Congress approved funding for these efforts. And most recently, in January of this year, NASA announced that they had contracted with the Defense Advanced Research Projects Agency, known as DARPA, and they would be collaborating on the development of a nuclear thermal rocket engine, and it would be tested in orbit by 2027. And the name of this concept is the Demonstration Rocket for Agile Cislunar Operations, or DRACO. The purpose of this, of course, is to develop a working system that'll be ready to go, hopefully by 2033, when NASA hopes to begin launching the first crewed missions to Mars. Now, in between and around all of that, there have been multiple proposals for novel nuclear systems that incorporate research, such as the NERVA program and other attempts to research NTP and NEP systems. In fact, earlier this year, as part of their NASA Innovative Advanced Concepts Review, a number of selections were made for further development that had nuclear propulsion or other nuclear applications in mind, one of which was for a bimodal system that would incorporate a wave rotor topping cycle. And this idea, according to the researchers, it could make the trip in 45 days, so roughly a month and a half. So this would be absolutely groundbreaking as far as missions to Mars were concerned or anywhere else in the solar system. That kind of transit time would effectively mean that all the challenges, all the health hazards, these would be minimized compared to existing mission architecture. Of course, the development process itself poses a whole other set of challenges, not the least of which is funding, and of course, whether or not it could be ready on time. However, NASA selected this idea, among others, for further development for a reason. And meanwhile, the UK Space Agency, or UKSA, as part of the European Space Agency, they're also researching nuclear propulsion technology. China is considering it for its own missions to the outer solar system. And there are also research proposals that consider equipping spacecraft destined for the outer solar system in the coming years, such as the Titan Dragonfly mission, how the spacecraft could be equipped with a nuclear propulsion system that would get it there much quicker. One in particular calls for a fusion reactor. And there, too, a lot of very interesting work is being done in that regard. And it is safe to say that beyond the current constellation of proposals, which all look to slow fission reactors to power a nuclear engine, fusion will be the next great leap. So systems that rely on the fusing of materials such as deuterium and using that energy directly as a propulsion source, these would be able to reduce transit times even further, and they will likely open the outer solar system to all kinds of research and quite possibly crewed missions. But in the meantime, getting to Mars, getting beyond the moon, achieving the great leap from the Apollo era and the space shuttle era to that next great step, that next great frontier, that will in all likelihood involve nuclear propulsion of the fission variety. Now, whether or not such systems will be ready in time for NASA's current plans for crewed missions to Mars, that remains to be seen. And there is quite a bit of doubt in that regard there. In fact, at the recent Achieving Mars Summit, in which industry experts and space agency experts and the scientific community and science communicators, they all came together to discuss all the possibilities, and it was the first time post-COVID that they had met. And from those who had attended, you would definitely get the impression that it was a very, very exciting time, and there was this huge sense of the possibilities. They're all coming together, and we're really starting to see movement, and we are roughly a decade away, and we can feel it. But on the subject of whether or not nuclear propulsion will be ready by 2033, there was no consensus. There was a lot of different opinions and different research that had been cited there that said, yes, no, maybe so. And there was also no consensus on whether or not a mission could be conducted that would be orbit only, which is what we would likely have to do if we cannot realize a nuclear thermal propulsion system in time, or something else that can ensure a much briefer transit window. But of course, the efforts to develop that kind of system, this kind of technology, they're really just getting off the ground. Even though so much of this goes back to the first space age, it managed to build a foundation, the creation of nuclear reactors that could be used in space, and in some cases were even tested in space, mainly through the Soviets' own efforts. As for the creation of a propulsion system, though, that relies on that, that's really just getting off the ground right now. So it'll be very interesting to see what happens in the next few years, and assuming that the funding environment is amenable, which will most likely require some hefty increases, we could be realizing nuclear rockets within a decade. And to say that that will be game-changing is basically to damn it with faint praise. It'll be beyond game-changing. It will be absolutely amazing, really. It will allow for so much, especially where crewed missions are concerned. It will mean that missions to Mars could get there within a matter of weeks instead of months, and missions to the outer solar system could get there in a matter of months instead of years. And combined with research into nuclear reactors, the applications of which are for habitats on the lunar surface or beneath the surface habitats on Mars, and any place where solar or wind power for that matter, is not a readily available option, or their limitations, which is certainly the case on both Mars and the Moon. These will provide a steady supply of power, which would likely be used not as a single power source, but to augment current systems, sort of an emergency backup. In the case of the Moon, this would be turned on every time the lunar night comes around, which is 2 weeks long at a time. So for 14 days in a row, you can draw on your solar panels for a steady supply of energy, but then for the next 14 days, you got to switch on that reactor. And NASA has been researching that through its kilopower program. And that has since yielded their kilopower reactor using Stirling technology, otherwise known as Krusty program. And the ESA and China are doing much the same. And on Mars, those same efforts envision nuclear reactors that will be there in case of dust storms or limited solar coverage or just low winds. On Mars, you can rely on a combination of solar and wind, but in the event that these aren't producing, the reactor is there to help meet the demands of the habitats. And much like nuclear thermal or electric propulsion, these are fission systems. So long-term, fusion reactors are likely to replace kilopower systems, and these could provide significantly more energy for base camps and also permanent settlements in the form of mini tokamak reactors, or some fusion concept that's very similar. So no matter how you slice it, nuclear power in space, it's something that we've been contemplating for decades, and it's very clearly the future of space exploration, and may very well be the key to expanding humanity's presence into space, becoming interplanetary, and creating quote-unquote backup locations for humanity. And like so many other things, we are alive at a time when that's really starting to pick up momentum, it's gaining speed, and we can look forward to some really exciting developments in the coming years. It may sound optimistic, but no matter what, it's going to be very, very interesting. So stay tuned for that. And in the meantime, thank you for joining me. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.